Hello everybody, how's it going today? My name is Connor, welcome back to another video. Today we're going to be talking about my newest project called PAPR. It is a audio processor runtime with its own scripting language, its own declarative scripting language in order to describe how these audio devices, all these digital signal processing devices kind of connect together. And it also has an environment to interact with those devices graphically via a GUI interface. So um, this is gonna be the first devlog where I just kind of talk about the parts of the project I have so far. It's definitely not finished yet. It is definitely something that's still in a work in progress. But yeah, so what I have done so far is basically a few different modules to this. I've created this interface to talking about the different types of signals that happen in digital signal processing. Um, and I've also created a interface for processors that implement the ability to process uh, signals, basically. So yeah. Anyway, let's get right into it. So I've got two main modules here that I want to show today. The first is this is the DSP module, and the second is the graph module. So um, first things first, when you're operating um, with digital signal processing, processors, you're typically going to come across two main types of signals, and this is mostly when you're working with audio or like things for making music, which is eventually what I want to do with this. Um, but yeah, so you're gonna have two main types of signals. You can have audio rate signals and you have control rate signals. And so the audio rate signals are the ones that are actually generating the audio that you hear out of the output of your speakers, right? Or whatever interface you're using in order to listen to whatever's going on in here, right? So and then you're gonna have control rate signals, which don't necessarily operate as fast as audio rate signals, because the audio rate signals, when you have a sample rate, how fast you're iterating through all the processors for the audio rate signals, and that can be upwards of many, dozens of times, dozens of thousands of times a second. Sorry. So like a common one is 4,000, sorry, 44,100 times a second. 44,100 hertz. I've actually been testing this at around 48,000 hertz, around 48,000 times a second. So that's how fast these audio rate signals are going to be updating, right? Is very very quickly. So otherwise, you won't be able to hear anything, right? And it needs to be able to move the speaker fast enough to actually generate sound signals, right? With enough fidelity. So but if you're doing something like controlling that signal with like a knob or with a slider or even with another signal, you don't always need it to be updating that quickly. So you also have control rate signals, which are an optimization in order to what's the word? Kind of like have a signal that's operating at a lower frequency. Sorry, I had a brain fart for a second. um, Basically just things that don't need to be updating 44,000 times a second go into the control rate, right? So things you're not actually hearing are control rate. Things that you do hear are audio rate. Make sense? So and I've created this generic type, this generic trait called signal type, which has one type parameter, one associated type, sorry, when that is a sibling node. And we'll get into that in a sec. But basically, I have two structs to implement this. Um, and one is the audio rate struct, which I use as a generic type parameter um, for audio rate things, and one is control rate struct, which I use as a generic type parameter for control rate things, right? So, let's see here. So, and then the sibling node is really just like whatever graph node type is associated with the opposite rate, you know, signal rate, right? Um, so, and I do that for reasons we'll get into in a bit. So I then have a signal which is just a holder for basically this scalar is just a synonym for a float. It could be a 32-bit or 64-bit float depending on cargo features. But this is a floating point value, it's a number. And then the signal is associated with a certain signal type, so a certain signal rate, or your auto rate or control rate, right? And this is the basic kind of building block that I pass around everywhere in my program. So yeah, so I can create new signals. I can create signals that, and importantly, the signal is parameterized by a generic parameter, which has to be one of these signal types, either audio rate or control rate, right? So it would look something like this if I were to actually instantiate it. If I were to like create a new signal that was control rate, it would be looking like that in the code, right? So same with audio rate. So I have a bunch of helper methods to helper implementations for common math operations. Okay, and then we get to the processor. The processor trait is another trait that is itself parameterized by this generic signal type parameter. So that means we can have audio processors and control processors. And the processor is something that can operate on on nodes, or sorry, it can operate on these signals, right? So it has two main methods, actually only two methods. It has process and then UI update, which UI update is by default implemented as just a identity operation. It doesn't do anything. So, and this process, it could be a bunch of different things. And a number of different things could happen in here. Anything that operates on the DSP logic itself is going to happen inside this method. So, I have like a bunch of other stuff that isn't important right now. So that's the DSP module that I wanted to go over, and I'm going to talk about how all these things are useful when I go into the graph module. So first things first, when we talk about having like a a, a setup of devices, right? You can think of it like patching together like guitar pedals, I guess, or like patching together like a modular synthesizer, if you're familiar with that. Um, you have all these different modules, right? That are all connected to each other, and some are connected to multiple devices. Some devices have multiple connections coming into them or out of them, and they can all be connected to different things. And so we have what's known as well, that can be represented very well as a graph signal. Or, sorry, I'm so out of it. As a graph data structure, right? I was like reading. Never mind. That can be represented as a graph structure, and what a graph looks like typically in computing data structures is something like this, right? And that's actually a graphic I was going to show later, but you can think of it like ignore the blue arrows for now. Just think of it like this is like a you have nodes that connect to each other and all different kinds of ways, and yeah, this is actually more of a tree, but so a tree is it's actually a type of graph data structure. So it's just a specialized type of graph data structure. Anyway, um, so and what I have here is actually called a directed graph. Actually, I should pull up a different graphic. You can hear my clicking new keyboard that I have now. Let's see, directed graph. Yeah, so directed graph has something like this, where a connection from like 1 to 2 is different from a connection from 2 to 1, right? So you see 3 and 4 are connected to each other in bidirectional way, whereas 1 and 3, 1 and 2, and 3 and 2 are only connected in a unidirectional way. So directed graph is where a connection from A to B is distinct from a connection from B to A. And that's important because we can use something like this to describe the flow of signals throughout a throughout one of these, signal graphs. So you can think of it as like, going back to this graphic again. Then we have like an oscillator on one, right? Like a sine oscillator. And then we have like a low pass filter or something on three. And then we have like that two that's like a your speaker, right? So we can have sine going directly to one speaker, or like the low pass filter going directly to another speaker. You get an idea, right? Um, so or yeah, something like this, where it's like this could be something that generates audio, right, or generates a control signal, and it could process it through these filters and or through these processors, and then each one goes on to a different processor until we finally reach the end, where we actually hear what's happening, right, or see it on the graphical interface. So, which, by the way, I should have mentioned this at the start, but I'm not going to show what it actually looks like yet because it doesn't really look like much. It doesn't really do much yet, but this is a lot of code that's kind of laying the foundation for kind of getting everything ready to be an actual usable application, right? So, um, anyway, so let's see, go back to. So that's what a directed graph means, and that's what I'm using for both the audio and control rate graphs in this application. And they run in parallel, right? So, and it's all using atomic operations to interface with each other on different threads. So, each graph has a number of nodes inside of it, and so I actually didn't stop. I want to talk about it anyway. Um, so a node is something like, again, going back to this visual, something like one of these, right? Where you have in the graph you have nodes and you have connections between those nodes. So the node can have some kind of processing logic in it. The connection uh, can store information about how it connects to each node, right? Like which input it's going into or which output it's coming out of, which is actually exactly what happens here. You have these nodes, um, and actually store the sibling node, the other node that, like, if it's an audio node, then I store the control node inside of it and inside of an atomic pointer, um, just so that I can kind of reference what's going on the control side of things. Actually, the control nodes actually do not have access to the audio nodes in most cases. Now, this option is going to be none for them, but um, either way, sometimes it might be useful. So I left it as like a terminology for like a sibling rather than just control node always, Anyway, and I have uh some inputs and some outputs to the node that can each have their own distinct names. So I'm using taking advantage of robust type system in order to kind of make it so that I can't mess up with passing like an input name to an output, something that expects an output, or an output to something that expects an input. So kind of these are all identical structs, but they all have distinct types, which means I can use them distinctly. So anyway, going back there. Um, so yeah, and then I have a pointer to the processor that is being used. Actually, it's almost a pointer, but either way, it's a processor can be something that it's just one of those processors that I talked about earlier in the DSP module, how it just acts on the signals in some kind of way. Now the catch to that is that the processors can actually also be graphs themselves, which I'll get to in a sec. Let's see. Yeah, so it can be either a boxed trait object or it can be a subgraph of the graph. So that's kind of like the aha, kind of like gotcha kind of thing. Um, so then I have this cache. So another optimization that I've decided to make when it comes to this the implementation of how these graphs run is I'm using a lot of caching. So and the caches are there in order to help reduce allocations happening at runtime or in real time, you know. Since those can be kind of slow, I know this from working on an operating system on my own, you know. The allocations can be slow, they can be not unreliable, but like, you know, if you can avoid having to do them, then that's usually a good thing. So wherever possible. Um, so here, um, so I have this inputs cache for every node, and I also have an outputs cache for every node, which actually lives on the graph for whatever reason. But should probably move that back into the node itself. But either way, so yeah, I just cache all the inputs and outputs of the nodes so that I don't have to reallocate those every single time I run the graph. So see here. So the graph itself, like I said before, is a processor. So let's go ahead and look at that. Yeah, so you can see, well, down here it says this is actual processor implementation, but it just calls this method either way. So, um, okay. Here's where we process and actually run through the graph, do a little search through the graph. And I wanted to talk about that as well. um, First things first, and I actually left little comments in here in order to help me remember what to talk about here. But first things first, if the graph is empty, we do nothing. You know, we don't have to return anything because we're being passed a mutable reference to our cache of outputs, right? So that can just be left untouched. Don't have to do anything. If we have nothing to do, then we don't do anything. You know, so it's not simple that way. We then copy the input values that are provided up here into our inputs cache for each node that is an input, right? So for each node that we want to have a new value inside of, we pass it into here, and we God, what am I saying? For each node that we want to have a new value associated with, or new value input into, we just copy it into our cache. Yeah, that's all that is actually. So, and then this stuff is very complicated, by the way. It's giving me a massive headache for the past. So it's kind of like helping me get it straight in my own head, right? So, then we do a breadth first search through the graph, and I want to talk about the difference between a breadth first search and depth first search, right? Because you didn't know either of those. So where did my web browser go? So yeah, here's where I was going to actually use this graphic. So I'm going to talk about why I'm doing a breadth first search and not a depth first search. Because my other project, Paddles, actually, the logic simulator, actually uses a depth first search, which I have now realized is wrong. So, why I actually want to do a breadth first search is because breadth first search, what it does, and it's actually really, really simple how it works, is you start at a start node, and you can have multiple start nodes as well. You just kind of push them into a queue of nodes to visit, right? A double-ended queue. And then for every node that's connected to that node, you visit them in order of, or in whatever arbitrary order, you know, just any outgoing nodes to that node. You then visit and you mark down the node that we've already visited as visited. And then what you do is you repeat that process for every new node that we've added into the queue. And that's literally it. So, and the advantage of this approach is that opposed to a depth first search, you can kind of see like the blue lines indicate the order in which we visit the nodes. So depth first search will will start at a node and then it will go down into one of its subnodes, right? But then it'll just keep going down, 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 further deeper into the graph. And that's a really good way to find like the shortest route through a graph for something. But if you want to make sure that everything happens in a certain order almost, then or like you want to make sure like all the prerequisites for a node, if it's like a prerequisite kind of graph, are handled, then you definitely want a breadth first search. Because what that does is it really kind of simulates like the flow of information through a graph. Right. You can see that first we process this node, node 0, then we process node 1, then we process node 2, right? And before we process node 3, we'll make sure node 1 is already processed in that regard, right? So even though we could, go directly into 3, we just want to make sure that you think about like water flowing down this graph, right? We want to go first here, then do both of these, then do all 4 of these, because all their prerequisites are met. So now you could technically, actually isn't a very good graphic for showing like the whole prerequisite thing because each one only has 1, so it doesn't really matter either way. But hopefully you get what I'm saying here. Like if this node had more prerequisites, then we would, as long as it was connected to the inputs, or if it was an input itself, then it would be processed before the node that depends on it. Make sense? Hopefully that makes sense. So, um, that's exactly what we're doing here. Is I'm using the pet graph crate for my graph algorithms, and I initialize this breadth first search, which is called a BFS in pet graph apparently. Yeah, breadth first search algorithm. It's not recursive. It doesn't, borrow the graph at any point. It literally just goes, okay, what nodes have we visited, and etc. So anyway, we start at the input nodes, the nodes that we've marked as input, and also the nodes that just have no inputs into them. And then we push those onto our stack of, sorry if you can hear my dog. Push those onto the stack of nodes that we're going to visit. And then we walk the breadth first search for every node in this graph in the order of source to output, right? Input output. We then for each of these nodes we copy the outputs of the nodes that feed into it into the input cache of the node that we're visiting. So like going we're copying the output of this into the input cache of this to get it ready to process, right? So that's all that is. We then create a copy of evidence from the cache because we're actually mutually borrowing self here, in order to get access to the output cache for that node. And then we run the processor logic, which is using that trait of implementing that processing logic. Like about in the DSP. Right here. Actually runs this method. So, and then as you can see, we're actually reading directly from the output cache for the input cache for the next node. So we just repeat this process until we've walked the entire graph. Have all the outputs for everything. And then we copy those cache values that are now updated inside the cache into the outputs of this actual processor. And that's it. It's really that simple, right? Just keep track of all the inputs and outputs of everything in this, except for cache. We don't use channels or anything. We don't use any kind of asynchronous or synchronization or whatever. All that stuff is basically opt in. If you want to do that inside a node or inside a processor, go for it. But there's no like there's a little bit of locking happening on inputs cache and outputs cache, but either way, we're only visiting one node at a time, so it doesn't really matter anyway. So yeah. Let's see. What else did I want to talk about? So that's just let's actually go through and talk about an example of some of these processors, and then we'll wrap up the video. So if we go into like this, ooh, that's not that. Okay. So let's talk about something like a sine oscillator, right? So first things first, we define an audio processor and a control processor for the sine oscillator. We then implement the audio rate processor for the audio processor. um, what we can do in here is we can actually access the sibling node because we are the audio processor. So this unwrap will always be successful. And then we can actually, from the sibling nodes, we can actually access their cached inputs. That's why we keep the extracted inputs on the nodes itself. So that we can, get access to extra parameters, like if we want to change the amplitude or frequency of this sine oscillator. Those are control rate signals. And so they're on the control node, but we can access them from the audio processor of the node as well. The audio rate node. So, and then we just do our little sine oscillator thing. We do our sine function, 2 pi times time step times the frequency. The t here is actually in seconds already, so I don't need to divide by the sample rate, but it's provided anyway, just in case I need it. So that's how you do a sine oscillator in hertz for the frequency. 2 pi times the time in seconds. We're good. And then the control processor actually doesn't do anything. All its inputs and outputs are, sorry, all of its inputs are going to be updated in the graph logic, and it doesn't have any outputs, so no need to specify anything there. And then up here we just have a helper struct for just sine oscillator to create both nodes at the same time. And it's a little complicated to do so, as you can see, but the idea behind this is that all this is going to be just what's happening automatically anytime you use the scripting language for this application. Remember, it's going to have like this very distinct scripting language as well, which I can actually show you a little teaser of what that looks like. I'm not gonna go over it right now, but it's like, this is basically, if you kind of get the idea of what's going on here, then let me know what you think it does in the comments. So anyway, that's gonna be it for this video. Thank you all very much for watching. I'm going to update you with my progress on this project in a bit. I actually do have a very basic parser working that actually will parse to run this, but I don't know if it's going to work right now. So I can try though. Let's see. See what happens here. The console log. It's not going to produce any audio, don't worry. Yeah. So you can see, actually will run and parse this script. Has a little debug output. Actually, if I change this to C0, then it should be able to see this number change down here if I move the slider on the interface. But this is a little teaser of what's to come. Yeah, so see now the value is 50, and as I move the slider, the value actually changes down there. So because it's all connected in the graph. Anyway, yeah, that's it for this video. Thank you all very much for watching. I'll catch you in the next one. Peace out. Oh yeah, if you like the video, hit like and stuff, and if you want to subscribe to my channel to see more of this stuff, greatly appreciated. All that jazz. Yeah, peace out.